All right, so today we're going to pick up where we left off. We finished with graphing points, and now we're going to move on to what does it mean to graph a line. So what I think where we left off before is by suggesting, okay, here is some coordinate system that we have. We know that we choose an orthonormal coordinate system so that the tick marks are the same size on both sides, and they have positive real numbers going in this direction, positive real numbers going in that direction, and then negative and negative down here. And we learned about like when we plot a point on it, what it kind of represents, and that we know how to add points together and so forth. And when you have a plane, there's no relationship between the x coordinate and the y coordinate. Okay, so this would be the real numbers here, and it will be in the x direction. That's an r. And then this would be real numbers here, and this is in the y direction, because that's what we choose. It doesn't have to be x here. We could call it whatever we wanted, but this is the coordinate system. So the x coordinate goes down on this axis because that's what we chose. The y coordinate is the height that you move along this axis. And when you just have ordered pairs, there's no constraint on it. And so all of these points that live on this whole plane are elements of things that you can reach through this coordinate system. But if you apply a constraint to this, then what you're doing is you're saying that there's some kind of limitation to where your points can be. How do you do that? What you can do is you can say, I want there to be some kind of relationship between x and y such that they're only allowed to have some kind of relationship with each other. So for example, the most obvious example is a line. You basically say, I want some number times x plus some number times y to equal some constant like this. So this is I think this is the standard form or the general form of a line. I think this is the standard form of a line. There's different names for, and I need to move my screen over a little bit. There's different names for what these things represent, and I can't always remember what they are. So you have this standard form or general form, and what it says is that whatever makes this thing true, it's going to limit what I can have for x and y. So I can't just put any value in for x and any value in for y, because I want this statement to be true. I want this equal sign to hold. And whatever this constant is, it doesn't matter. It could be 0, right? You could move it over to the other side. So by forcing this statement to be true, I might be able to choose x to be any value that I want, but it constrains what value y can be in that case. And so what this is going to end up doing is taking what would be an entire plane and dropping it down to being a line like this. So this is going to be one of these lines. And there's different ways of representing lines. One of the ways of representing a line is the way that I showed, ax plus by equals c, where a, b, and c are constants. You could also have a line that looks like this one. Okay, this is where you plot y is the vertical axis, and you have y is equal to some function of x. Okay, and this is what the function of x looks like. Okay, both of these things are valid. It's fairly easy to transform between these different ways of representing a line. Another way to represent the line would be to start with the line basically x plus y equals something. How do they do this one? It's the point slope form. So the point slope form is that you start with this form here, and then you shift it. So you shift it up by some amount, y minus k, and you shift this function over by some amount equals f of x minus h. So this is the point slope form. And what that turns into, if you put all this up here, is that you end up with something that looks like y minus k equals m x minus h plus some other number over here. Actually, you don't, in this case, this turns out to be 0. So this thing ends up being 0 because you shift it up by that amount. So this form here is the point slope form. You have a point, hk, that you know lives on the line. You have a slope that's related to that line. And so given the point and the slope, you put it into this form, and that's the equation of a line. All of these things, you can interchange them. You can do algebra to both sides of this equation and get it into any of the forms that you want. The point of this is that when you have y equals some function of x, now this is a constraint. It constrains what you can have for the different values, and so you no longer can explore all the points in the whole space. You can only explore points that satisfy that constraint, and those points all lie, in this case, on a line because of the nature of this particular letter here. So when you take a plane, and you place a linear constraint on it, so that's one of these ax plus by, y equals c. A linear constraint meaning that these things are all to the power 1. Then it takes you from a plane and gets you a line. So you've gone from a 2-dimensional space down to a 1-dimensional space. Okay? You could imagine a situation where you place 2 constraints on your space. So you could say, I want to have not only this equation be satisfied, but some other equation be satisfied, like dx plus ey equals f. So this is a second constraint on the universe of places that we live, or that are allowed in our 2-dimensional space. And this is the first constraint. So the first constraint might give us something that looks like this. Those are the points that satisfy this constraint. You have another set of points that satisfies this constraint. It might look like this. And because these 2 constraints are different, there can only be one place where both of them are satisfied at the same time. So this one will give you that constraint. This one will give you this constraint. And where both of them are satisfied is the one location where those 2 things cross. Now, this is because these are linear equations. If we have more advanced or higher order functions, then you can get different results, but we're not there right now. So what happens with each of these constraints, you reduce the solution space from a 2-dimensional, like a full 2-dimensional plane, down to a 1-dimensional line, and then finally down to a 0-dimensional point. Okay, so there are different ways, algebraic ways of solving 2 equations and 2 unknowns. One of the ways to do it is to say, so this is where you get a system of equations, where you have ax plus by equals c, and you have dx plus ey equals f, and you need to find the one location where both of these equations are satisfied. You can have a situation where they might trick you and you get 2 lines that lie on top of each other, or you can get 2 lines that are parallel to each other. Those are kind of special cases. I mean, they're important to know about, in which case you get infinity solutions or you get no solutions. So you can either get infinity solutions, no solutions if they are parallel, or you get 1 solution. Those are the only choices you have. With lines, you don't get multiple solutions. Well, unless you get all of the solutions. So if it's degenerate, then you have infinity solutions. The 2 lines are actually identical to each other. That would be the case if you had like x plus y equals 1. That's an equal sign. And you had 2x plus 2y equals 2. So these are degenerate solutions. If you had 2x plus 2y equals 1, then you'd have parallel things. The slope is the same. The ratios of these coefficients is the same, but this quantity is different, so that gives you parallel lines. But if these 2 numbers are not multiples of each other, then you'll get a line that comes off at a different angle, and therefore you'll get a single point. So when you're solving for systems of equations, you want to find the solution where both of these equations are satisfied. You're taking all possible solutions, which is a whole plane, reducing it down to the intersection of 2 lines. And so one of the ways you can do this is to basically take one of these lines and substitute it into the one down here. So basically in that case, and I'm sure we've seen this before, you might take one, put it into the y equals mx plus b form. You take the other line, you put it into the y equals m2x plus b2, and then you set these 2 things equal to each other. You set this y equal to that y. So you have 2 lines, you set the 2 lines equal to each other, and then you solve for x. And what are you doing in that situation? You start like this. You have one line that goes like this, and it's in the slope-intercept form. You have another line that goes like this. It's also in the slope-intercept form. And by setting them equal to each other, you're saying, I want these y values to be the same. What is the location where the y values are the same? When you set this y value and this y value equal to each other, you're saying, I want the point on this line, the vertical point on this line, and the vertical point on this line to be the same. And so that says these 2 things are the same right here. So that forces you onto this line here by setting those two equal to each other. And then you just say, okay, what is the x value where that happens? And so then you have this final equation, mx plus b equals, that's a b, equals m2x plus b2, like that. So that forces you to be at this height, forces you to be at that height because the y values are now equal to each other, and then you solve for x. And so then you come over here and you say, when does that actually happen? And then that gets you this x. And so you plug in x, you get x, now you need to know what is the value of y, and so you take that x and you put it back into one of these equations, and it will either, depending on which equation you substitute it into, you'll either get the y from this line, or you'll get the y from this line, but we know that they're both the same because that was, when we set them equal to each other, we forced them to be the same. So visually what you're doing when you do the substitution method of solving for a variable and sticking it in is you're saying, I want to force these two things to be equal, or force them to be, the y, in this case, the y values to be equal, and then I'm going to solve for the x where that happens, and then I'm going to find out what the y is, and now I've got the point xy, where those two things intersect. You can do it the other way. You can solve for x first, so you get x equals and then something, 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 and then you can get the other equation where it's also going to have x equals something other, something other, something other. And in that case, graphically, what you're doing is you have this line, and you're saying, I want the x values to be the same, and then you're solving for, you find out, you set them equal to each other, and then you solve for y, and you get the y value where that happens, and then you substitute back in, and then that returns the x value. So you force it to be the same, you solve for the other variable, and then you substitute back in to measure what the first variable is. So that's basically what you're doing in the substitution method. There are other ways of doing it where you can kind of transform the coordinate plane, but in all these cases, a system of equation is, here's one constraint, here's another constraint, is there a place, and where is it, where both of those constraints are satisfied simultaneously. The equal sign, when you set them equal to each other, that's where you get the simultaneous solution. Now, if you go to 3 equations and 3 unknowns, so if you have ordered triples, x, y, and z, now instead of being a plane, you're talking about a whole space. So you've got this whole volume. You can have points all throughout this 3-dimensional volume, and a single point is going to be some location in a 3-dimensional space. Now, we usually think about these as 3-dimensional physical spaces, but it could be, 3-dimensional mathematical spaces related to different physical quantities like kinetic energy, potential energy, or whatever. When you place a constraint on a set of ordered triples like this, so a constraint would be that you want it to satisfy some relationship. A linear constraint would be ax plus by plus, that's a y, plus cz equals d. So this says, I'm going to restrict my 3-dimensional space down to the place where this thing is satisfied. And what it does is it collapses you in 1 dimension. So now you get a plane that slices through. So here is your plane, and here is your coordinate system. And the plane is going to be coming through at some kind of weird angle relative to everything. It's, so for example, this could produce, the plane could look like that. The plane that produces that triangle. So here's a plane that kind of cuts through space. That's what x having something like this does. So if you're doing systems of 3 equations and 3 unknowns, then you have another equation and another equation, and that would correspond to, you have a plane that cuts like this, for example. You have a second plane that cuts at some other angle like that, and these 2 planes are going to intersect along that line. When you have 2 planes intersect, so these are both 2 dimensions, and you have them intersect with each other, then you're going to get a 1-dimensional result that comes out. If you have a third plane that comes in at some third angle like this, it's going to intersect also at that line. So the intersection of these 2 planes is going to be a line like this. The intersection of these 2 planes is going to be a line like that. The intersection of these two planes is going to be a line like this. And there may be only one location where all 3 of those planes exist at the same point. Like there's a point that belongs to all 3 of those planes. So that's what you're doing when you're solving for 3 equations and 3 unknowns. You can see that a single plane, if you have an intersection of 2 planes, you get a line by looking at, how about if you look at my Physics 182 exam that I gave before. So I'm going to take 2 planes and intersect them. Let me switch my field of view. to not that. I want to switch my field of view to this, like that. Okay, here we go. This is going to be amazing. So here is, there's one plane right there, one plane right here. So there's this plane, and there's this plane. And when they intersect, so now I'm taking two planes and they're intersecting, they intersect on a single line. Right? That line where the fold is the intersection of two planes. Isn't that amazing? So whenever you force a constraint on something of a given dimension, the allowable space that returns is one dimension smaller. Thank you, Doggy Don't. I appreciate that. Let's see. Where else do we go from this? So that's basically all that stuff. If you have a higher dimensional curve, so this was with lines that you get something that looks like that. If you have a higher dimensional curve, then you end up with a different shape. So if you have y equals some function of x, where this function of x is like x squared or something like this, then you get a curve that looks more like that. Okay, well in this case you get a curve that looks like that. And here, it's not a line anymore. And so when you're setting these functions equal to each other, it's still, okay, let me rephrase it again. It's not a straight line anymore. It is a line. You have some constraint that you're imposing on something. You do collapse the allowable space from a two-dimensional space down to a one-dimensional space, but that one-dimensional space is on a curved path as represented in this plane and not on a straight path. So a linear function will give you something like this. A quadratic function will give you a curve that looks like that. If you set two functions equal to each other, in this case, then you can end up with places, for example, where there are two solutions. Okay, or if you have a higher order polynomial that looks like this, you can set up a situation where in this case, there'd be three solutions, where that line and that curve intersect each other. You could imagine setting up a curve where, it goes like this, and you have a line that comes through and actually only produces two solutions. Okay, or you can have a line that comes through and only produces one solution, like that. But that requires, what we're talking about here is a higher order equation, not a set of lines. And so the next part of the book goes from graphing lines to, let's take a look at what happens if instead of linear functions, we have higher order polynomial functions. So we need to understand how polynomials work before we can start graphing polynomials and then seeing what are the relationships that you get when you have one polynomial and one polynomial constraint on the space and one linear constraint on the space. So those are the questions that will be coming up